Hi, I'm Christian, member of the Customized High Performance Computing Group, and today I will present you one very specific application which we have brought on the Sync device. You will learn about option pricing in finance. You will learn about how to design a very advanced Sync system which is configurable, reconfigurable, and you will learn about how to apply all you have learned kind of from the low level that Mohammad Sadri presented and also from the methodology level that Christian Schreiber presented, how that integrates into a real design. So before we go into design itself, let me show you some kind of background information about option pricing. So why are we even talking about option pricing and FPGAs? Here are the facts. So when we look at the stock market, 70% are traded, 70% of the stocks are traded via computers. And we have several financial institutions, and each financial institution has 2,000 so-called exotic options traded every 5 minutes. And these exotic options, they have to be evaluated with very advanced models. And to do that, they have big clusters. And here we have one financial institution which has a 2,000 node IBM cluster, and the energy consumption, just the energy consumption, is vast. It's 20 megawatt hours per day, which equivalents to around 1,600 households, 4-person households per day. And we have, in the world, we have 1,000 similar institutions. So what do we learn from here? From here we learn that option pricing demands very high compute resources, and that's what makes an FPGA acceleration so attractive in terms of energy savings, also cost savings. So what is an option? What is an exotic option? Let's start with the most simple option. And here we have the Xilinx stock index, and it's currently, we say it's about what do we have here? 2014, we'd say. So if today is 2014, we have right now a price of $42. And now we look into the future, so September 2015. And with the option, we can claim a right to buy. So we can say we can buy the stock index for the same price as it is today, also for $42 in 1 year. And now two things can happen. Either the stock price goes up, and then we can do a trading. We can buy the stock with our option for the cheaper price, $42, and we can sell it for $54. And with that, we made a profit of $10. If the stock price goes down, we do not issue it because we can buy it cheaper on the market, so we don't have to exercise our option. And so with the option, we can kind of make a bet on the future. We can make, when the stock price goes up, we make a profit. When the stock price goes down, we make no profit. So we always make a profit with the option. And that means the option will cost us some money. And the question is, how much money does an option, how much worth is an option? So there are many different models how you can do that, and the banks have come up with very advanced models. So, but even looking at this simple stock, you can see, okay, the stock price tends to go up. So the average price, the average profit will maybe be about $5. And that's probably a good fair price. What are banks doing? Banks have developed, and also financial mathematics have developed several models to model the stock price in the future. One of them is the Heston model. And the Heston model is more advanced than its state-of-the-art model that many banks are using for more advanced option pricing. And it consists of two differential equations here on this side. And it's a stochastic process. And it models different probability density functions, as you see here on the top. And when you apply this model to the stock we see here, you get something like this. So you get this probability density function. And it models the stock price in every moment in time, like this, every moment in time, with a probability density of how likely is it to get a different price. And to evaluate the fair price of our option I showed you before, you can just kind of average up the prices at the end and get your average price. These models normally don't have a solution, an analytical solution. And that's why people are using Monte Carlo simulation and other numerical methods. And when you use Monte Carlo simulation, you can rewrite the equations in kind of a discretized form. And then what you get out of are very individual paths. So you basically simulate the market for many, many different scenarios. And if you do that often enough, you can make claims about the average. And here you see some of these paths, and for us, the average profit is $5 if you evaluate this model. So what are the challenges in the Monte Carlo method? The biggest challenge is to control the errors in the Monte Carlo setting. In principle, it's very simple. So we have the price, the option price P, which is kind of, we take the stock, S, we take the payoff of the stock, and then we take the expectation value. So it's kind of the expected payoff of the stock. In a Monte Carlo setting where we are averaging over a finite number of paths, and in addition, we don't take the payoff of the stock S, but the payoff of a discretized path. Because as you can see already here, stock prices can get arbitrarily complex. And when we simulate a Monte Carlo path, we have to kind of account for only a finite number of discretization points, like 10 or 20 or 100 or 1,000. So we have two kinds of errors. One is that we only use finite path. That will give us a statistical error. And the second one is we only have k discretization points, and this will give us a discretization error. The total computational cost of Monte Carlo in this setting is n times k. So we have n paths and k discretization points, which can get really, really big very, very fast, because normally the paths are in the order of millions and discretization points in the order of 1,000, 10,000. And so, instead of using classical Monte Carlo, and that is something we will see again and again in many, many applications. When you go to acceleration, you really want to make sure that you are using the most efficient algorithm. So in that sense, we are not using the first algorithm that does the job, but really the most efficient one. And the classical Monte Carlo I've showed you is quite crude, and there are many, many additions, many, many more advanced schemes available in the financial literature. One of them I will present here is the multi-level Monte Carlo method. And it works like this. So here on this side we have kind of the standard path of the crude, the classical Monte Carlo method. And instead of simulating millions and thousands of this path, we rewrite it. So we do several independent Monte Carlo simulations. On the first level, we kind of simulate very coarse paths. So we simulate paths with maybe only 4 discretizations. And then we do a second Monte Carlo simulation where we simulate kind of the difference between a path of a higher discretization and a lower discretization. So in this case, maybe 16 and 4. And we simulate only the difference and the payoff of this difference path, and so on. And with that, we get kind of an initial estimate from this Biscombe Monte Carlo simulation. And then we get kind of refinement factors, correction factors, which make our result better. No. So why is this so attractive? First of all, the level 1, we have very cheap paths. So the path to simulate, it's order of n times k. So k is very small, so these are very cheap paths. And for high levels, typically, the variance tends to go down because the differences between the paths is getting smaller and smaller. So the correction factor also has a lower variance. And if that's the case, we have to simulate less paths. So n is much smaller. In that case, we have an overall lower computational cost by doing this hierarchical step of Monte Carlo simulations. There's another challenge in when we build an option pricing system. What I've shown you so far is kind of, I showed you the simplest option there is, a call option. I showed you a model on how to get the fair price of this option, the Heston model, how to evaluate it, the Monte Carlo method, and a more advanced scheme of doing that, the multi-level Monte Carlo method. Now, there are many, many different options. We have the call option, we have the look-back option, we have Asian options, we have Berry options, and they use different features. Like the call options, it only uses the payoff at the end, at maturity. The look-back option looks at the maximum, the peak of the stock. Asian options look at the average of the stock. Berry options look at if a barrier is hit, the option is getting worthless. So we have a huge variety of payoffs. And these are all part of our equation and part of our solution of our Monte Carlo method. So in that sense, it can be quite challenging to design a system which covers all kind of options. Now, let's ask ourselves how we put that application onto an FPGA. I've now covered the background, I've talked about options and so on. Now, how do we develop a powerful, efficient option pricing system? And first of all, on the Zynq and also Hyper targets hybrid systems. And we will see later why that is. But for now, hybrid systems are very attractive. And a hybrid system consists of a CPU, an interconnect, and an FPGA. The CPU is very flexible, and the FPGA is very efficient. And by combining both of them into one system, we get kind of the best of both worlds. To model our architecture, we use a platform-based design methodology. And it works like this. So we have here kind of the application space. In our case, it's financial option pricing. And it covers all the different options we have in our system, like Berry options, look-back option, and so on. That's all part of the application space. And then we have kind of our architecture space. And the architecture space is consists of different reconfigurable hybrid systems. So we already know that for the Zynq. When we have the Zynq, there is not one Zynq chip. The Zynq is really a family. So we have different devices with different FPGA size, different CPU power. We have Zynq Ultrascale. We have also other vendors like Altera offering similar devices. And that's all part of the architectural space. And Hyper is really a platform. We see it as a platform that generates us an efficient solution given a very specific option and a very specific architecture. And then it generates us hardware and software for that specific case that is most efficient. That's what we call a platform-based design methodology. And it comes with three features. Hyper comes with three features. One is we have a modular option pricing system here, number one. The second part is we have systematic feature extraction. And the last part is we have a static optimizer. So let's look at these three things individually. The first one is the modular pricing architecture. So, when we looked at Monte Carlo, kind of the most basic computational step is to generate the paths. So we generate the different paths, millions of paths, and then we average over the payoff of these paths. That's what we do. And in our architecture, we go path by path. So we generate one path, we calculate the payoff. We generate a path, and to generate a path, we do this step by step. So that's kind of the discretized Euler scheme. You start with the initial point of the stock price, and then you go to the next point, and you go to the next point, and you go to the next point. That's how you can discretize a differential equation. And that's what our FPGA has to do in its heart, to have this path generated. And actually, it's also one of the biggest blocks in our architecture. The path generator, as you see here, takes two random numbers to come from the initial point to the next point. It takes two stochastic, because it's a stochastic differential equation, it takes two random numbers, which are generated in an increment generator. And in our case, it's a Gaussian random number generator. Out comes logarithmic Monte Carlo paths. And from then on, we take the exponential of these paths to get the Monte Carlo path. We calculate the payoff, as you see here, and then we make the statistics to get the mean and the variance. And after that, we have kind of the result of one Monte Carlo simulation. And in the case of multi-level Monte Carlo, we can then run the different Monte Carlo simulations, one after the other. One thing to note here is that these blocks have different flow control. So the first blocks, as you see here, the increment generator, path generator, and also the exponential, they operate all on path level, on steps level, on steps of paths, one step after another. While the last two blocks, here the payoff and the statistics, they operate on paths. So they take one path after another and they take it. When we have a closer look at the payoff, this is kind of the link in between. It takes Monte Carlo steps, one step after another, and at the end we get one number from each path, kind of the payoff in dollars, as a result. So inside of it, we have a formula that does that. And we can look at it in a bit more detail. And here's one example, it's the Asian option. So what is an Asian option? I told you about that before. It takes the average of the stock path, and that's basically the payoff. So that's what you see here. It takes this is kind of the time value of money. Then it takes the maximum of the average of the stock minus the payoff, and if that's bigger than 0, that's your payoff. So in that equation, we can split it up into a path-dependent part and a path-independent part. The path-dependent parts are parts that depend on the path itself. And in this case, it's only the sum. So only the sum depends on the path. And all the rest, like the maximum, the exponential, the difference, the multiplication with 1 over k, depends not on the path. It only depends on features of the path. So that's what we do. For each payoff, we can split it up into a path-dependent and a path-independent part. The path-dependent we call features, and the path-independent we call payoffs. Now, why is this interesting? Now we can go through all the options I've showed you before, like the look back, digital, call option, barrier, and so on, and we can extract the different features. And here you see kind of all the features we have extracted from these simple options, from these options we have seen. And here are the payoff functions. So we have barriers, we have arithmetic features, we have trigonometric features, we have min-max features, and value at maturity. And these options can even combine different features, like we will use the geometric mean, but only if it doesn't hit a barrier. So the payoff might use multiple features. And financial practitioners are very, very elaborate in inventing new options to model different kind of trades they want to do and model different kind of risks. And for that, our practitioners can now use this systematic feature extraction process and find new features and put it into our architecture here and create new payoff function here. And in fact, we will see later, we will model these blocks as in HLS, in high-level synthesis. And if you have seen high-level synthesis, it has a C++ interface. So you can write equations like barriers and arithmetic mean in a very straightforward way. So it's even possible to write a very simple domain-specific language which uses basically just a template, and where practitioners can put in the equations, so they don't have to use any VHDL knowledge or any kind of FPGA knowledge. They just have to write an equation in C++, and we can write a simple generator which then generates all the rest of the interfaces and puts them into our architecture. In this case, we are looking back at the flow control. We call this the hyper front end, the increment generator, the path generator, and the features. And the back end, we have kind of the exponential, the payoffs, and the statistics. And now we can pull everything together. So we can now combine different front ends with a serializer to one back end, because the back end is much, much slower operating, so it can process several front ends. As I said before, we are using a hybrid system. And in a hybrid system, we can make a hardware-software splitting, as we call it. Parts that we put on the FPGA and parts that we put on the CPU. And a very straightforward hardware-software split would now be to put the front end on the FPGA side and this back end on the CPU side. And this is a good choice for many, many Monte Carlo simulations. There's one exception. In the multi-level method, we have seen that the very first Monte Carlo simulation used paths which very, very low discretizations, like only 4 discretizations. And in that case, every 4 steps we generate features. So our backend has to process a path every 4 steps. And if we have 4 front ends, the back end is as occupied as the front end. So in that case, we also have to put that back end on the FPGA side. So in that case, we already see that the hardware-software split depends on the level we are at, and it also depends on the option we are having. Like if we have a very, very simple option, like a call option, we might be able to do that on the CPU. But if we have a very, very complex option with complex sine and cosine stuff and logarithmic functions, the CPU might be too slow, and we also have to put that on the FPGA. So the hardware-software split depends on many, many variables. That's why we use an optimizer. We don't have to make this decision all up front. We don't have to do it now. We can leave it to the platform. So the platform decides at runtime how to partition it. And we can model that with an optimizer. The goal of the optimizer is to maximize the hyper performance for a specific platform and for a specific financial product. under specific constraints. What is the freedom the optimizer has? So the freedom is the number of hyper instances, number of hyper front ends, how many front ends to put on one back end, where to do the hardware-software split, also which communication core we use between FPGA and CPU. Do we use a DMA? Do we use register transfer? They all have different pros and cons. And also how many hyper instances do we put on our FPGA. And it has different constraints. One constraint is kind of the FPGA area. The FPGA is limited. The other one is the CPU load. The CPU is only as powerful as it is. We cannot put more on it. The bandwidth between CPU and FPGA, and that might depend on the core we're using. And also the flow rate. So when we put something on the FPGA, it has to go in synchrony. And our optimizer has to know that. We can use an ILP solver to solve this optimization problem. And with that, we can get different FPGA configurations out of that. For each level. So for each level, for each option, for each platform, we get a different FPGA configuration. And that's the point. So let's look at Hyper on Sync. How does it work on Sync? The Sync has two cores, two CPU cores. It has an FPGA fabric, and it has an on-chip interconnect, all on one chip. We look at the following example. We look at barrier options in our application space, and we look at the Sync 7020 for our Hyper system. And we use the Hyper platform now to generate us optimal configurations for that platform. So what do we need? What have we done? So we have, it all starts with the blocks. So we have our modular pricing system. We have programmed it in HLS. Each block, I've showed you the path generator, the increment generator, the random number generator. We have modeled it in an HLS core with AXI interfaces. A known HLS project, a known block on the FPGA. And also, you know that HLS uses C++ code. So we can use these cores directly, or we can write a different code if we want, and run that on the CPU. The same code, the same block. Okay. So with that, we can now model the system. So for each of the blocks, we can run a synthesis for our specific device, the Sync 7020, and get kind of the area numbers. How many bloods, how many flip-flops, how many DSPs, how many block RAMs. We can also run the different blocks on our CPU and get kind of the CPU load it generates. So how many nanoseconds does it need on the CPU per value to run this kind of block, kind of per input value. And also we can look at kind of all the different bandwidth options we have on our Hyper system for serial FIFOs, for DMAs, and for register access. And we can even automate that. So once we have that, we can write a script that automatically models us a specific system and hooks up on all the synthesis tools, on all the benchmarking tools on our CPU. Then, once we have these numbers from our system model, we can then put that all into our optimizer. So the optimizer now gets these models and also the kind of the product we want, because the product tells the optimizer which kind of blocks do we want to put in, which kind of features, which kind of payoffs are part of the architecture. So it can build the architecture for this specific product, and then it can find the best FPGA configuration. So exploit all the freedom. How many front ends per back end, how many instances where to put the hardware software split, and we can do that for each level. And that's what we get here. And you will see here we have, this is for level 1, we have kind of 4 front ends for 1 back end, and then it's fully utilized. We have another front end with a partial back end, and everything is sent to the CPU where kind of the last bit of the back end is done and all the controls done. For higher levels, it looks different. Here we have, this is kind of a multi-level. We have to simulate 2 paths, so they are a bit bigger. So we only have, for level 2, we only have 4 front ends and 1 back end, all on FPGA. So everything is on the FPGA. And for higher levels, for level 3 and onwards, we have only the front ends on the FPGA, as you can see here. And then we use the DMA to transfer all the data and do the back end stuff on the CPU. So we get kind of 3 configurations for all of our levels, and we can generate a bit stream out of these configurations, which we can reconfigure over runtime. And this can all be automated. Now, how does that system perform? So here we have 2 axes. We have once the flexibility axis, which tells us basically how easy or how hard is it to put a new option, a new product into our FPGA, into our system, into our pricing system. And on the bottom, we have kind of the runtime here. And the runtime is really in minutes. To price 1,000 options with 120 watts, so with the same power budget, and also at the same accuracy, because we are now comparing different schemes, and we have to guarantee that they're using the same power and the same accuracy. We started with the classical Monte Carlo scheme, and that's what many financial institutions are still using. That's our first example was about. And we run it on a CPU, an Intel i5 mobile processor, or you could say energy efficient Intel i5 processor. And it's very flexible. It's very easy to add options to that, and it takes 470 minutes. And we are using here, in that case, we use about 4 CPUs. So we use a system with 4 CPUs. Then we have looked at the multi-level Monte Carlo method. And on the same system, it gets a speed up of 3.8x. It only takes 125 minutes. It's a bit less flexible because it's a little bit harder to integrate options. You have to make some tests to see if it works. But it's still very flexible. The next thing we looked at were classical Monte Carlo on the Zynq FPGA. And this is really putting everything on the FPGA. And we have seen research papers that have been doing that. We have done that on our own. In our case, we got a speed up of 12.7x over the multi-level Monte Carlo setting. And in that case, we use a stack of FPGAs, a stack of Zynq FPGAs to get to 120 watts. One thing to notice here is that all the flexibility has been lost because it's very hard to integrate a new option. If the payoff changes, if the feature change, we have to basically reprogram the FPGA, we have to reprogram the VHDL, we need an expert, and so on. So that's what we tackled with Hyper. With Hyper, we created this platform and the systematic feature extraction, which makes it very easy for practitioners to adapt options or to add new options, because everything else is automated. So we get back the flexibility. And in addition, we are the first time we're using multi-level methods, and we get another 2.8x speed up from using the multi-level method. In addition to that, we also looked at mixed precision ideas. I just want to mention it here. I have not presented it here, but what the basic idea is, we have kind of the different Monte Carlo levels. You have seen the cores and then finer corrections. And the point is, we don't have to use floating point on every level. that we're using in the multi-level hyper, and also on the CPU we're using floating point everywhere. But on the FPGA we can now use a reduced arithmetic. And it turns out we can use different precisions for each level. So we can use a very low precision on the first level and then higher precisions on higher level. And we published a paper on that. It's called Mixed Precision Hyper, Mixed Precision Monte-Carlo Levels, Monte-Carlo Methods. It's here, you can see it. And with that we get another 2.1x speed up. And with all of that we are down to 1.7 minutes, which is a total of 280x speed up. So that really shows the power of using FPGAs in a very intelligent way. You get a 200x speed up in energy savings and also runtime savings. Another thing I want to mention here on the top is we have published a demonstration about that. We've showed it at several conferences, and there's also a YouTube video about that. We'll link to it on here. So you can click on it if you're interested in the running system. And we also have published the source code of this demonstration, and it contains most of the part of the Hyper platform that you can look into it. We will put that into the description of this video. Furthermore, there is a white paper on how to set up all of this, how to set up the demo, how to set up the repository, how to program the device, how to generate the bit stream. There's a white paper, 8-page white paper, which explains different parts of the platform and how it all integrates into another. One very interesting aspect you might want to look at is we used Linux, Linaro Ubuntu on the CPU side of the Zynq. So it's very easy to program. You can even use Python, you can use C++, you can use GCC, you can log in via the terminal, and you can run different scripts. And we even found a way, and also Xilinx supports that, to reconfigure the FPGA from the Linux. So you can type in a command and it swaps the bit stream. And that's also part of this repository, and it's all explained how to do that, how to set up the Linux, and how to reconfigure the FPGA bit streams, how to generate it with the tool, and how to put them onto the SD card, and how to generate it in real time, and how to swap between the bit streams. So that's something you might want to check out. Now, let me conclude what I have told you about. And I want to really stress some lessons learned. This work has been very, very exciting for me, and I've really seen the power of the FPGA, a new power of the FPGA. The first thing that I learned is how powerful it is to optimize on algorithmic and implementation level at the same time. So often as hardware practitioners, we are too quick at implementing one algorithm. And here we sat together with mathematicians and really asked and explored are there more advanced schemes to do it even in pure arithmetic level? Are there algorithms with less complexity? And that's always worth it, and we see it here what you can get out of that. The next one is really to use the FPGA only for what's really needed. So the big power of the FPGA over ASICs and other non-reconfigurable devices is that we can change the configuration during runtime. So we don't have to create a generic architecture. So we don't have to generate an architecture which can price all levels, which can price all options on the stock market. We don't have to do that. We don't have to put that into the FPGA. What we can do instead is we can only put the parts that are necessary at this time into the FPGA. Now, why is it so hard to do that? Or one thing, if you want to do that, one thing that's very helpful is to build platforms instead of generic architecture. So as I said before, generic architectures, we don't have to do them. Now, what we replace them for is platforms. So the flexibility is not in the FPGA architecture itself, but it's in the platform. And the platform then generates us architectures once it knows all it needs to know during runtime. So once it knows which kind of option do we have, which kind of FPGA architecture do we have, once it knows that, it generates all that is needed to be done on the FPGA, it generates a new configuration and uses that. And I just want to mention here, FPGA synthesis time is still quite large, so it can take several hours. But when we look at the applications we looked at here, the high-performance computing applications, it's often the case that they are doing the same thing over and over again with different data. So even if there are hundreds of options, one option is priced several million times a day on different stocks, on different dates, and so on. So with that, we might end up with maybe a couple of hundred or thousand configurations, but not infinite. We don't need a new configuration for every new run. But this platform allows us to abstract from that and generate us configurations for maybe a subset of the application space. And also, it's very powerful to use the CPU for all the control decisions. So we can put the optimizer on the CPU, and it can do all the control decisions, and it's very, very easy to do that in a Linux system on the Sync device. So with that, thanks for listening, and see you in our next episode.